Hello, my awesome chemists. Hope you're having a great day. We're going to start talking about chapter 15 today, which is equilibrium. And equilibrium is a very big topic in chemistry. Make sure you're reading your learning objectives. And equilibrium has to do with reversible reactions. So most chemical reactions are actually reversible. There are a few that are not, like combustion reactions, for example, are not reversible, but the majority of reactions are. So a reversible reaction means it goes both ways. So your reactant particles react together to form products, but then your product particles also react to form back the reactants. And like I said, most reactions are reversible somewhat. And you reach equilibrium when the forward rate is equal to the reverse rate. So what that means is that the rate of the reactants reacting to form products is equal to the rate of the products for reacting to form reactants. So for every reactant molecule that I use up to form products, one of the product molecules is used up to reform the reactants. So we call that a dynamic equilibrium. Dynamic means changing. Equilibrium obviously means equal. And so it's equal in that the forward rate is equal to the reverse rate. So the rates of the forward and the reverse reactions are equal. We call it dynamic because the particles are constantly changing. The reactant molecules turning into products, the product molecules turning into reactants. So the particles are continuously changing. The reaction is going on, but it actually looks to us like it had stopped because there's no change in concentrations. There's no change in appearance of the reaction because, again, the rates are equal. So for every reactant molecule that's used up to form products, a product molecule is used up to reform the reactants, and so the concentrations and everything else remains the same, even though the reaction is still going on. So it's called a dynamic equilibrium. Now, for the reaction to reach equilibrium, the reaction needs to be in a closed system, meaning your conditions should not change, and no particles should come in, no particles should leave. Your system is enclosed, and your conditions should remain the same in order to get it to reach equilibrium. And in order for it to reach equilibrium, a certain amount of time has to elapse. And that's what we talked about in chapter 14 with kinetics. How fast does the reaction occur? What that means is how fast does it go from the start until it reaches equilibrium when the forward and the reverse rates are equal to each other. So a certain amount of time has to elapse in order for the reactant particles to collide and form products, and then the product particles collide and reform reactants, and then your forward and reverse rate are equal. The kinetics of the reaction, how fast it happens, has to do with activation energy, like we learned in last chapter. So the higher the activation energy, the slower the reaction. The lower the activation energy, the faster that reaction. So this has to do with kinetics. Activation energy has to do with kinetics and how fast it reaches equilibrium. In this we already talked about it in chapter 14. In this chapter, we are going to talk about more of what happens in terms of rates and concentrations and things like that to the particles when you reach equilibrium. So let's look at this reaction here. We have hydrogen reacting with iodine to form hydroiodic acid. Hydrogen and hydroiodic acid are colorless, but iodine is purple. And so when you react these together, because the reactants and the products have different colors, you will see a change in color initially as you start your reaction until you get to equilibrium. Once you reach equilibrium, though, the color will remain the same because, again, the forward rate is equal to the reverse rate. So every time I use up these two molecules to form 2HI, I use up 2HI to form an H2 and an I2. So the concentration doesn't change once you reach equilibrium, and so to us, with our eyes, it looks like the reaction has stopped, even though it still keeps going, but the rates are equal. So let's talk more in detail about the change in concentration and then in change in rate from the start of the reaction until you reach equilibrium. So here is a data table. It gives us time, and then it gives us the concentrations of the reactants and then also the product. So let's start with concentrations. At the very beginning of the reaction, you only have reactants, right? There are no products at the very beginning if the reaction has not started yet. So my reactants concentration is really, really high, and my product concentration is basically 0, okay? As time goes by, I have lots of reactants at the beginning, but they're going to get used up to form products. So as I go through my reaction, my reactant concentrations are going to get smaller because the reactant particles are being used up. So you're going to see something like this. Okay. And then once you reach equilibrium, the concentration of the reactants does not change. It remains the same. And so it continues steady like that. Let's look at the products. At the beginning of the reaction, there were no products, but as the reaction went on, some of the reactants got used up and formed products, and so my product concentration started increasing, as you can see on my table here. And then once you reach equilibrium, it just remains steady. Okay, so at the beginning of a reaction, you have high reactant concentration. As the reaction goes by, that reactants decrease, and then once you reach equilibrium, it remains steady. For the products, they start at 0, they increase as the reaction goes by, and then when you reach equilibrium, their concentration remains constant. The concentration of the reactants and the products are not usually equal to each other at equilibrium, but they remain constant. These are your products, and these are your reactants. And here is where you've reached equilibrium. You know that because your concentrations are not changing. They're not equal to each other, but they are constant. And in this case, it just so happens that my product, my HI, has a higher concentration than my reactants. And so my products surpass in concentration my reactants. That's not always the case. So it is possible that you get some curves that look like this. This would be the reactants. This is the products. These are their concentrations and time. And so in this specific reaction, at equilibrium, you have more reactants than you do products. That happens. It is possible, it's rare, but it is possible that you do get, just by coincidence, the reactant and the product concentration. Sorry, no, I can't draw. These are overlapping here. So these are your products. These are your reactants. So it is possible. It's pretty rare, but it is possible that for a specific reaction, you get the same amount of reactants and products at equilibrium. It would look like this. But most cases, you have more products than reactants or more reactants than products once you reach equilibrium. But what is the same about all of these is that once you've reached equilibrium, the concentrations of the reactants and the products remain constant. Okay, let's talk about rates. How fast the reaction is going, the forward and the reverse reaction. So at the beginning of the reaction, you only have reactants, right? You only have H2s and I2s. And so the forward rate is going to be pretty high because there's lots of reactant particles that can collide together and form products. So your rate is going to be pretty high for the forward reaction. As time goes by, because you now have used up some of the reactants to form products, you have less reactants, and so less reactants able to collide together and react, and so your forward rate slows down. Once you reach equilibrium, the forward rate remains constant. So this would be the forward reaction rate. At the beginning, pretty high because all you have is reactants, lots of reactants. But as the reactants concentration gets smaller, the reaction gets slower because there's not as many reactants to collide together and react. And then once you reach equilibrium, the rate remains steady. For the reverse reaction, so going from HI back to H2 and I2, well, at the beginning, you have no HI to react, right? So your reverse rate is 0. You don't have any molecules to react. And so it starts out at 0, but as the reaction goes by and I now have some HI forming and increasing, then the rate of their reaction increases, so the rate of the reverse reaction increases. And then once you reach equilibrium, it equals to the rate of the forward reaction. So for rates, it is always going to look like this. No other choice. The forward rate is pretty high at the beginning, slows down, becomes constant at equilibrium. The rate of the reverse reaction starts at 0, increases, and then remains constant at equilibrium. The forward rate and the reverse rate are equal at equilibrium. Not the concentrations, but the rates. So this is where you are at equilibrium. Forward rate is equal to the reverse rate. Okay, so down here is basically what we had just talked about. So it walks you through basically these two graphs here, or sketches. So at the beginning of a reaction, the reactant concentration is really high, and therefore the rate of the forward reaction is pretty high. At this point, the product concentration is very low. You don't have any products, and so the rate of the reverse reaction is also very low. As the reaction proceeds, the reactant concentrations decrease, and therefore the forward rate also decreases. For the products, as the reaction goes by, the product concentration starts increasing, and the reverse rate starts increasing as well. When your reaction reaches equilibrium, that's when the forward rate and the reverse rate are equal to each other, and that's when equilibrium is established. So your forward rate and your reverse rate are equal to each other, and so because of that, your product and reactant concentration remain constant. They're not equal to each other, but they are constant. It's the rates that are equal to each other. So on the macroscopic scale, on the big scale, to us it looks like the reaction has stopped, but in reality, if you look at the microscopic scale, so if you look at actual particles, particles are changing all the time. Reactants are turning to products, products are turning to reactants.